Year 12. Because this paper is so long, I've actually completed it before I've started filming, so that you don't have to wait while I'm busy writing and calculating things out, and I'll just be explaining it. So hopefully that will speed things up a little bit. The first question was a data analysis question, and the first mark was literally for drawing a best fit line. Just make sure it's a nice crisp thin line there, smooth, and it passes through all of the error bars. The next bit of the question asked you to state how you know that the line of best fit suggests that H mean is not proportional to T, and you both said correctly that it is not a straight line. One thing that you mentioned is that it doesn't go through the origin. Well, you actually can't be sure of that because your graph does not show the origin, so you don't know, so don't mention that bit. Then the uncertainty in each value of T. So if you look really closely, sorry, mine's printed half size, but each error bar either side of the point on T is half of a small square, which is 1 degree Celsius. So it's plus or minus 1 degree, not 2 there. Then the next question was a little bit tricky to interpret, I think. So the temperature is measured using a liquid and glass thermometer. State what physical characteristic of the thermometer suggests that the change in the liquid's length is proportional to the change in temperature. Okay, so let's get our head around this. So in a thermometer, we have some liquid in the bulb at the bottom. And as the temperature increases, the thread of liquid starts to move up the tube, the capillary tube. Okay, so you know that on a thermometer, the markings are evenly spaced. So as you go up by a set distance, you must have gone up by a set temperature. And that shows that the length is proportional to the change in temperature. You've got that equal gradient there. So something along the lines of each increase of 1 degree Celsius is equally spaced on the scale along the tube. And because it has a constant cross-sectional area, it must be increasing in length by the same amount for the same temperature change. Then you had a calculation question, quite a lot to this actually, 4 marks. Let's see if I can fit all of it on the page. So it tells you an equation for H mean is given by KT cubed, and K is a constant. And you have to calculate the absolute uncertainty in K. Now in order to do that, you're also going to need the value of K. So that's maybe the first bit to point out. K is equal to H divided by T cubed, and we're doing this for when T is 50 degrees Celsius. So we literally read off at 50 degrees Celsius and get our value for H mean, and that's 0.72. And we can also look at the size of the error bar at this point as well. And that's important because we're going to get the absolute uncertainty in H mean from the Y error bar and the absolute uncertainty in T from the X error bar. So that is our K value, and then we need to work out its absolute uncertainty. So if we rearrange the equation we've been given here to make K the subject effectively, because we know we're doing H divided by T cubed, we are going to add the percentage uncertainty of H to 3 lots of the percentage uncertainty in T. Okay, so what I've written here is the fractional uncertainty in K is equal to the fractional uncertainty in H plus 3 lots of the fractional uncertainty in T. Okay, so at the point where T was 50 degrees Celsius, the error bar for H was plus or minus 0.01. Okay, so you just had to read this bit off the graph. So therefore, the uncertainty is 0.01 out of the 0.72, which was the value. And we're not timesing by 100 to make it a percentage. at this point, I just want to point out to you that this is the fractional uncertainty. Okay, and then we do it for the temperature as well. We know it's plus or minus 1 degree Celsius. And the value, excuse me, yawning, is 50 degrees Celsius. And we multiply that by 3. So we get the fractional uncertainty in T here. Okay, now we know that the percentage uncertainty in K is equal to the sum of those two percentages. So I've just multiplied by 100 to turn those into percentages. And that's how I get my 7.4%. But remember that it asks for the absolute uncertainty. So I then have to find that 7.4% of my K value. And this is what you should end up with. And they are also giving a mark for having the correct number of significant figures and a unit. Now, because your H values were given to 2 significant figures, I think that's our smallest, we gave it to 2 significant figures. And then that's meters per degree Celsius cubed for your unit. Okay, question 2. So we've got a pendulum. You can see the time period of the pendulum is given by this equation, and it tells you that g is acceleration due to gravity. So I have immediately squared both sides just so that I don't have a square root to deal with. I find that easier. And it asks for the fractional uncertainty in g. So what I've done is I've rearranged this equation to get g. Okay, so I get 4 pi squared L over T squared. Okay, now 4 pi is a constant, so it doesn't contribute any error. It's just a mathematical number. So what we're going to end up with is our uncertainty in L plus 2 lots, because it's T squared, of uncertainty in T. Okay, and it gives you the values of the uncertainties and the values themselves, and you end up with this fractional uncertainty. Now, because it is a fractional uncertainty, don't convert that to a percentage. So on your calculator, this might be given as a fraction. You can then just write that as a number. That's absolutely fine. Okay, question 3. Alright, we've got a company delivering packages to customers using a small unmanned aircraft. I think Amazon tried this for a while. Rotating horizontal blades exert a force on the surrounding air. The air above the aircraft is initially stationary. Okay, the air is propelled vertically downwards with speed v. The aircraft hovers motionless above the ground, so it's not moving. Okay, a package is suspended, blah blah blah. It gives you some mass values. We'll come back to those, but the most important thing is the first thing it says: state the value of the resultant force on the aircraft when hovering motionless. A stationary object has no resultant force, so you just needed to say 0. Okay, then it asks you to outline, worth 2 marks, how the upward lift force on the aircraft is achieved. Okay, now we know that Newton's third law says that if A exerts a force on B, then B will exert an equal and opposite force back on A. Okay, so if we're looking at the upward lift force on the aircraft, we have to think about the opposite force provided by the aircraft on the object that provided the lift in the first place, which is the air. Okay, so what we want to say is that the blades of the aircraft exert a downwards force on the air particles. According to Newton's third law, this means the air particles must exert an equal force upwards on the blade. So we've got our first statement, our second statement. So pause if you need to. Okay, now this bit was a tricky one, this next bit. So it asks you to determine V, so state your answer to an appropriate number of significant figures. So let's go back, we're looking for V. So let's have a little look at the information they give us. So it says the package is suspended, the mass of the aircraft itself is 0.95 kilograms, and the package is 0.45 kilograms. Okay, the mass of the air pushed downwards in 1 second is 1.7 kilograms. Okay, so let's have a look. We know that in 1 second the total mass pushed down is 1.7 kilograms. Now I've actually drawn this at the bottom because there wasn't enough room. We know that the system is hovering. Okay, it's not moving. So the total momentum of the entire system is 0. Okay, that's important because we have no net movement. Therefore, the change in momentum of the air, which is moving down, must be equal and opposite to the change in momentum of the blades. Okay, because we want that sum to equal 0. So, force multiplied by time of the blades must be equal to the force times time of the air. The impulse has to be the same, the change in momentum. And that must be equal to m air v air, mass times velocity, okay? Because the initial velocity of the air is 0. So the change in is just the final momentum, okay? And we know that this is occurring in 1 second for us to be able to have a mass value, okay? So because we're told that it's 1.7 kilograms in a second that have been moved, we know that the T for the blades must also be 1 second. Okay, so we'll come back up here. The force on the blades and the package is the weight down. Okay, that's the force that the blades feel. That's our total mass. Here's G. Okay. We know this, by the way, because for the package to not be moving, the weight, which is mg, must balance that force up. Okay, which is the from the air. And this is the one that we're comparing to the force and the momentum change from the air particles as well. But because we know they're equal in value, because this thing's not moving, that's why I'm choosing to write mg here. Okay, so I am considering the force on the blades from the air, but I just know the value is equal to the mass times gravity. Okay, so here is our force. Our time was 1, so if I put t, that's just 1, so that goes away. That's why I haven't written anything. Okay, and then that's equal to mv minus mu of the air, but remember that u was 0, okay, because the air is initially stationary, so you just get 1.7v, and then you just rearrange and you get a value for v there. Okay, then in 3D we've got a package and string are now released and fall to the ground. The lift force on the aircraft remains unchanged. Calculate the initial acceleration of the aircraft. Okay, so the weight acting down is now smaller because we've lost the 0.45 kilogram package. So the force down has now got smaller, but the lift up, we're told, stays the same. Okay, so the resultant force on the thing that gives the acceleration is the difference between the lift and the weight. It's the lift up minus that weight there. Okay, so this is our resultant force. So that was our lift value from before. that's our weight. And then the mass is now just of the drone, whatever it was called, the thing hovering, just of that itself, so the 0.95. Okay, and that gets us our value there. Alright, let's look at number 4 then. Okay, so this one starts off quite straightforward. So we've got a bob, it's swinging, it has 75 grams of mass, and when it reaches the object it's moving to the right with 0.8 meters per second, and this thing is stationary. They then stick together and then they start to oscillate backwards and forwards. So it's a simple conservation of momentum to start us off. Momentum before is equal to mass multiplied by velocity, mv, but we only have movement in the bob, so that's the only bit of momentum we've got before. And then afterwards they stick together, the bob and the object, so the mass becomes the total, which is 2 lots of 75 grams. Don't forget to convert it to kilograms, multiplied by v, and then you rearrange and you get 0.4 meters per second. And then you are asked to prove that the collision was inelastic. So that was just finding the kinetic energy before the collision, which obviously comes from the bob that's moving, and then the kinetic energy after. And then you see that they are not the same, and so you say therefore we have an inelastic collision. Sorry, my dog is just poking his head outside. He might start barking. Okay. Next bit then, sorry this is all over the place, it says describe the changes in gravitational potential energy of the oscillating system from t equals 0 as it oscillates through the cycle of its motion. So I've sketched it out. Starts from the centre, moves out to the extreme, comes back to the centre, moves out to the extreme on the other side, comes back to the centre in one full time period. So we just want to say that gravitational potential energy is minimum while the system is at the equilibrium position, or the centre, and it is maximum when the system is at maximum displacement. Okay, and this maximum and minimum value of gravitational potential energy will occur twice during one oscillation. So you'll get 2 maximum GPE values and 2 minimum GPE values. Okay, so question 5, we've got a chicken's egg, it's 58 grams and it's dropped onto grass from a height of 1.1 meters, plural, and the egg comes to rest in 55 milliseconds. Assume that air resistance is negligible. That tells us that there's no energy loss to the surroundings, that's important, and that the egg does not bounce or break. Okay, so the first thing we can work out is that if it's dropped from rest, here's my little egg, we can find the velocity of the egg at the moment it reaches the ground, because all of the gravitational potential energy gets converted to kinetic energy. So I equate the two, I'm told the height, I know the mass, I can get an expression for V. I guess it's best to just pause when you're copying the numbers down. Then I know that the egg is going to go from this velocity to rest, okay, because it stops, it says that. So therefore I can find the change in momentum of the egg, okay. That will be from the instant it comes into contact with the ground to it stopping dead, okay. So we're actually finding the momentum change effectively at what looks like this, from the dark grey sketched egg to this white egg. Okay, it's not the momentum change from up here to down here. Okay, because it has to be when the ground is in contact. So, change in momentum, mv minus mu, must be equal to impulse, which is force, multiplied by time. If I divide by time, I'm left with the force. So, final velocity is 0, so final momentum is 0. Initial momentum is the mass in kilograms multiplied by the velocity that I found. Divide that by the time. So, in order to get the egg to come to a stop, we effectively need 4.9 newtons as our resultant force. We know that that is going to come from the resultant of the forces acting on the egg. Okay, so we've got the force pushing up from the ground. Always sketch this out, it'll help you figure it out. And the weight acting down. Okay, but overall, what we need from these forces is 4.9 newtons to bring it to a stop. Okay, so that must be equal to the force from the ground minus the weight. Okay, to get our resultant force up that slows it down. Okay, so then you rearrange this and you get the force from the ground, which obviously has to be larger to account for the weight. So you add the weight to that resultant that you need, and you'll get that force from the ground. Okay, in part B, it asks you to explain why the egg is likely to break when it's dropped onto concrete from the same height. Now, there are a few misconceptions with this one. So, we know that the egg has fallen through the same height. Okay, so we know that the egg has the same velocity at the moment it hits the concrete compared to where it hits the grass, right? It's sped up by the same amount, it hits with equal velocity, and it has to come to rest. So both eggs in concrete and grass have to change their momentum by the same amount, because they have to come to rest from the same starting momentum. We know that that change in momentum is equal to the force multiplied by the time. Okay, and we know that the time in which the concrete is in contact with the egg is much smaller because it's an inelastic material, whereas the grass is a bit spongy. So that makes the force much larger for the concrete, and that's therefore going to make it more likely to break. Okay, question 6. Okay, so we've got a double slit experiment. Notice that there are some dimensions on the diagram that you're probably going to need later. So we are told that theta is the diffraction angle there. So it says a series of dark and bright fringes appears on the screen. Explain how a dark fringe is formed. Now this is just in general. Okay, so in general, how do we get a dark fringe formed on the screen? Okay, so the first thing we want to say is that there will be superposition of light from each of the slits. Okay, that's the first thing. Then you mentioned that this will cause interference between those two light waves. And then thirdly, if light from each slit meets up or superposes with a path difference of an integer value of lambda over a half, they will destructively interfere. Okay, so you've got to have n over 2 lambda as your path difference to create a dark fringe. Okay, then it tells us that the wavelength of the beam is 633 nanometers. Be careful here. The separation between a dark and a bright fringe on the screen is 4.5 millimeters. Now, for our single slit diffraction, the angle gives us to our first minima, right? But when we're looking at double slit and we're looking at our double slit equation, so S is lambda d over d, you need to be careful because this S represents the distance between two bright fringes or two dark fringes. So we have to multiply by 2 to get our fringe separation value. And then it's just a case of rearranging and plugging the numbers in. And you will get your value of 4.27 meters. Okay. Then let's have a look at the next bit. The air between the slits and the screen is replaced with water, and they give you the refractive index of water as 1.33. And they ask you to calculate the wavelength of light in water. So, we know that the refractive index is the ratio of the speed of light in a vacuum compared to the speed of light in a different medium. And we also know that speed is given by, or V, is equal to F lambda. Okay, so I know then that C is just a constant value, it's 3 times 10 to the 8, and the frequency of the light is not changing, nothing tells us that that's changed. So N must be proportional to 1 over lambda, or wavelength is inversely proportional to N. Okay, so what that means is there's a constant of proportionality, K, in here, and what that then means is K must be equal to lambda N, and that must be a constant. So lambda air N air must equal lambda water N water. Rearrange, we've got all of our values because we know the refractive index of air is 1, and we can get our value for wavelength. Okay, again this question was a bit tricky because you misread it. So state 2 ways in which the intensity pattern on the screen changes. It doesn't say how can you change the intensity pattern that in the generic sense. It's asking what will happen to the pattern because we've now got water. Okay, so we've just worked out the new wavelength, which is clearly smaller than the original wavelength. And so now we use our equation again and say, all right, well, the wavelength has got smaller, so the fringe separation S must also have got smaller. Sorry, I'll come into focus in a second. And then the other thing to think about is what we know about the electromagnetic spectrum. Okay, so if you think about it, when the wavelength is really, really small, we've got like gamma rays and X-rays. And then when the wavelength is really, really large, you've got microwaves and radio waves. We know that these are the most energetic ones, okay? So therefore, if the wavelength has got smaller, there's more energy involved. So there'll just be a more intense pattern. The intensity will be higher. Okay, let's look at number 7, standing waves. Okay, so a loudspeaker is emitting sound. This is important. The position of the loudspeaker is to the right of the pipe. So the air is moving backwards and forwards, left and right. Okay, all along this pipe, air particles will be vibrating left and right. A standing wave is formed in the pipe, and you can see the molecules of air and their displacement at one instant in time. For part A, outline how a standing wave is formed. You just need to say that there's an incident wave from the speaker and a reflected wave that bounces off the close end of the pipe, and they interfere. Okay, and when they interfere, they've set up this standing wave. So that's A there. Give you time to write that down. Okay, then for part B, it asks you to draw an arrow on the diagram to represent the direction of motion at molecule X. Alright, now what you might have got confused by is this y-axis is telling us where in its cycle it is moving from left to right. Okay, so we're repeatedly cycling around this. Okay, at position X, at this instant in time, we track up and see that X has been displaced to the right. Okay, but it hasn't reached its peak position to the right. So if this is its original position, it's travelled a little way, but it hasn't quite reached its maximum displacement before it comes back yet. So therefore, it must still be moving to the right. So we just need to draw an arrow to the right on there. And then the next bit is just labelling a node. That's pretty straightforward, where you've got an equilibrium position. You could also have chosen here. And then, last but not least, it asks you to calculate the frequency of the sound. So it tells you the speed of the sound and the length of the pipe. Now, hopefully you can see that inside the pipe is 3/4 of a wavelength. And it tells us that this is 0.3 meters from here to here. So an extra quarter is going to be plus 0.1. So 1 full wavelength is going to give you 0.4 meters. So then you just plug it in to your speed equation for waves. Rearrange, so frequency is wave speed divided by wavelength. You're told this value in the question, and you should have worked out the wavelength, giving you the frequency. Okay. Ignore the diagram for now because I've done the part F, but we're not quite there yet. So we're told that the loudspeaker is emitting sound into air, but there's then a boundary where we meet water. We've got wavefronts, and originally you could see these bits. So then it says the speed of sound in air is 340 meters per second, and in water it is 1500 meters per second, so it's sped up. Okay, so the wavefronts make an angle with the surface of the water, determine the maximum angle at which the sound can enter. So what we are trying to find is the angle of incidence, so that's this angle here, where you still get refraction and not total internal reflection. So at some point this angle will get too big and it will reach the critical angle and it will bounce back instead of entering the water. Okay, so that would be I is equal to the critical angle in that instance. Okay, and we know that n is equal to 1 over sine of the critical angle. So the refractive index that we're looking at here for the air is equal to 1 over sine c. Okay, so we know that we are looking for the refractive index of the water. We're going to see that that is the ratio of the velocity in the water compared to the velocity in air, giving us 1500 over 340, so we're told our values. Okay, giving us our refractive index of water. Then we can equate that to our critical angle, and we get an expression for critical angle, and we'll get 13.1. Okay, now remember that this is refractive index for sound, not light, so that's why the values are not what you're used to, because we're looking at sound here. Okay, so sorry, this should say n of air, got distracted here. So n is c over v, c is the water, the faster one, v air. So that then gives us our angle. Then the question underneath is asking for you to draw lines on the diagram to complete the wavefronts when the angle is smaller than the critical angle. Okay, so that means that refraction has occurred and it hasn't totally internally reflected. So what I've done is where wavefront C reaches the boundary, I've drawn the normal line. Okay, then you need to find 90 degrees from the wavefront, and that means that this set of wavefronts mean that the wave direction is along this pink line, which is also parallel to the direction that you're getting from the loudspeaker as well. But I'm just putting it here so that we can draw our refracted wave ray at that point. Okay, water is clearly a faster medium than air, so therefore it will move away from the normal. Okay, so if this is your incoming wave, it will move away from the normal. And then your final step is to find 90 degrees to your final direction of travel, and that gives you the angle at which you're going to draw your new wavefront. Okay, and then you just keep that parallel and move it along to each wavefront and draw your lines there. Okay, question 8 then. So it's a copper wire. Sorry, just wait for it to focus. And it has many copper wires inside. So it's a cable with many copper wires inside and an insulator around the outside. So it says the copper wires and the insulator are both exposed to an electric field. Then discuss, by referencing the phrase charge carriers, why there's only a significant current inside the copper wire and not the insulator, despite the fact that they're both in an electric field. So 3 marks, 3 points. Copper has free electrons. Insulating materials have very few free electrons. Electrons are the charge carriers, that's important to identify, and are accelerated by electric fields. Therefore, only the electrons in the copper can move. Okay, but you have to state that you recognise that electrons are the charge carriers here. Okay. Then it asks you to calculate the radius of each wire given some values. So we take our resistance equation with resistivity. We recognise that cross-sectional area is pi r squared because we need the radius. And we substitute pi r squared into A here. And that will give us an expression for R. Okay. And then you just plug your numbers in and you should get your value. Just take a minute if you need that. Okay. Then it tells us the current total in the cable. So remember that that's going through all of the individual copper wires. And each copper wire is effectively a resistor, okay, because it's a length of a conductor that has resistance value. Show that the power loss in 1 metre of the cable is about 30 watts. Now, previously we are told, if I go back quickly, each wire has a resistance of 64 ohms. That's important. Okay. So we have 30 wires inside the cable rather, each with resistance 64 ohms. And so to find the total resistance in the cable, we have to find the parallel combination. Okay, so 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. Okay, now we know that we have 32 cables, we're told that, and we know that each of them has 64 ohms of resistance. So we've got 32 lots of 1 over 64 plus 1 over 64 plus 1 over 64, etc. Okay, so if I then flip both sides of the equation, I get our total, and that's 64 over 32. Okay, so the total resistance of the cable is 2 ohms. So then, to find the power loss, I do P equals I squared R. I'm told the current here, and I've just worked out the total resistance. Okay, and that's a really large number, but that cable was 35 kilometres long. It told us that in a previous bit of the question, and it only asks for the power loss in 1 metre. So I just divide by 35,000 metres, and I get 30.5 watts. Okay, then in the next question, you've got an electric shower with a power rating of 8.5 kilowatts. It's connected to 240 volts, and you're given some values for length, area and resistivity, and you're asked to find the power dissipated in the cable. So I would use I squared R. I know that I is equal to V divided by R, but it's also equal to P divided by V, and those are the values that I've got. So power was 8.5 kilowatts, voltage was 240. So the current must have been 35 amps. Okay, so that's where I get my 35 from. And then I need to find my resistance. So that's the rest of this stuff here. That's going to come from our resistivity equation. So we've got resistivity here, the length is 10, and the cross-sectional area is given in millimeters squared. So we need to convert that into meters squared. So we know that 1 millimeter, is that still showing? Not quite, is equal to 1 times 10 to the minus 3 meters. Okay, so 1 millimeter squared is equal to 1 times 10 to the minus 3 all squared, which is equal to 1 times 10 to the minus 6 meters squared. Okay, and I've got 6 millimeters squared, so I'm going to have 6 lots of this. Okay, so I get 6 times 10 to the minus 6 meters squared for area. And that gets my resistance, and then that's all of this bit here. When I do this sum, I get 35 watts. Okay. So just to be clear, this bit is equal to 0.028 ohms. Okay, that's R. Okay. Question 10 then starts off pretty straightforward. You've got a pretty basic circuit with a cell, an ammeter measuring current, a variable resistor, and a voltmeter measuring the voltage across there. A voltmeter that is ideal is one that has infinite resistance. That's what you need to say there. And then they are going to adjust the variable resistor and collect some readings for voltage and current. Okay, so you've got voltage on the y-axis, current on the x-axis, and the first thing it asks you to find is the EMF of the cell. So that's going to be the voltage supplied when the current is 0. Okay, so you just read your y-intercept, and that's going to be 9 volts. Okay, when no current flows, there's no internal resistance effectively, so the voltage is the EMF. We know then to find the internal resistance of the cell, the EMF is equal to the current multiplied by the total resistance of the circuit, where R is the resistance of the external circuit and little r is the internal resistance. Okay, if I expand this out, I capital R is the terminal PD, so that's the voltage that is supplied to the variable resistor. Okay, and then I little r is the voltage supplied to the cell itself because of its internal resistance. Okay, I know that this is what's on my y-axis, and I know that I is on my x-axis. Okay, so what I'm going to do is I'm going to rearrange to get it in the form of y equals mx plus c. V is equal to the EMF minus I little r. There's y. We've just said that EMF was the intercept, it's plus c. X is our I, and therefore the gradient must be the internal resistance. So all I've done is I've taken 2 points and I'm effectively finding this gradient here. Okay, you can choose any 2 points but make them as large as possible, and you will find that your internal resistance is roughly 0.8 ohms there. Okay, then in part C you're asked to calculate a drift velocity or a drift speed. So you just take your drift speed equation, rearrange it to find V, and then you're plugging numbers in. So current is given is 3.5 amps, N is the number of electrons per unit volume, you're given that there, A, the cross-sectional area, you calculate from 1.2 millimeters, don't forget to convert it into meters, pi r squared, and then your charge of your electron. You'll get a value of 2.01, and then you say that is approximately equal to 2 times 10 to the minus 4. Okay, that was quite straightforward. Then you're given a wire, it's got current flowing into the page, so your middle finger goes into the page with your left hand rule. Your magnetic field goes along with the field arrow, and your thumb, which you can hopefully see is pointing down the page, gives us the direction of the force, which is one thing you're asked for, so down the page. And then the magnitude of the force comes from F equals BQV. So we've got B, flux density of 0.25 Tesla, Q is the charge on the electron, because we know it is a current carrying wire, so it has to be electrons, and then B you've just worked out up here as 2 times 10 to the minus 4. Plug it all in and you get your value for force. Okay, question 11, let's have a look at this one. Alright, so they were lenient, but the examiners pointed out that what they actually really ideally wanted to see was a line that was drawn with pencil and ruler, so that it was a very straight line, and it had to very clearly, for the force, it had to cross through the centre. So draw it as large as possible, I guess, up to the centre, to make that really obvious. And then again, you just need to make sure you've got 90 degrees between your force and your velocity arrows. So that's the first bit. Then it tells you the speed of the proton. So that's its tangential speed, so this velocity value here at any given point. And the field strength of 0.042 Tesla. So, for this proton, determine in meters the radius of the circular path. Give your answer to an appropriate number of significant figures. So, look at the values you've been given, and the smallest number of significant figures is what you give to, which is this one, it's 2. Okay? So, we know that the centripetal force, which is equal to mv squared over r, must be provided by the magnetic force, so it's equal to BQV. Okay, so all we do is we rearrange this equality here to get R. So hopefully you can see that we end up with mv over BQ. And then it is just a case of plugging the numbers in that you're given, and then making sure that you give that to 2 significant figures. So pause if you need to. Okay, in 11D it says calculate in seconds the time for 1 full revolution. So you're going to need speed as distance over time. You know the tangential speed, so you have to work out the absolute distance travelled in 1 full revolution. So that's the circumference, which is 2 pi r. And so therefore the time is going to be equal to your 2 pi r, your circumference, your distance, divided by your speed, which you were given at the top of the page. Okay, and again, to 2 significant figures, that gives you 1.6 times 10 to the minus 6. Okay, number 12, we're getting there. So, we've got Phobos. Yeah, hopefully I'm saying that right. Phobos. It's a moon of Mars and it's orbiting around Mars. It has an orbital period of 7.7 hours and a radius of 9.4 times 10 to the 3 kilometres. Notice this. Everything needs to be in metres, so you're going to need to multiply by 10 to the 3 again later in order to get your values in metres. So, outline. Y Phobos moves with uniform circular motion. Okay. So we can say, firstly, Phobos's weight, due to Mars's gravitational field, provides a centripetal force, firstly. Okay. Then, this force is at 90 degrees to the direction of the velocity, okay, meaning it does no work on Phobos. So, it doesn't accelerate. the velocity will stay the same. Hence, it moves at that constant velocity, thus proving it's uniform. So it's identifying what provides the centripetal force, then explaining that that force is acting at 90 degrees to the velocity, and therefore the velocity value remains constant. Okay. Then in the next bit of the question, it asks you to find the orbital speed. Okay, so that's the tangential speed. V is r omega. Okay, where omega is 2 pi over t. T was given to you, but it was given in hours, so you need to convert that to seconds. And r you were also given, but you just need to make sure that you convert it into meters to make sure you get all your numbers right, although you are lucky because it then does ask for it in kilometres per second, so that was very kind, but they could very easily trip you up. Sorry, Cameron needs to go back and focus. So just always get into the habit of getting into meters per second first, and then if you need to go back to a different unit, that's absolutely fine, and then you can prove that that is about 2 kilometres per second. Okay. Next bit of the question is that it asks you to deduce the mass of Mars. Okay, so we know that the centripetal force, mv squared over r, is provided by the gravitational force of attraction. Okay, gmm over r squared. Cancel the two little m's and rearrange. Okay, then just plug the numbers in and make sure you get the right value. Again, this is why it's helpful to have put it into meters per second for V, so that you don't mess up and put 2 here. Okay. 13a is just one you just, by now I'm sure you know. The conditions for simple harmonic motion, we've got acceleration has to be proportional to displacement from the equilibrium position, and that the direction of that acceleration is always towards that fixed rest position. 2 marks, easy peasy there. Okay, then they're going to give you a mass spring system which is oscillating in simple harmonic motion. Okay, and in your data booklet you are given this equation. Okay, this is the time period for a mass spring system. Okay, time period, mass, K is the constant of proportionality here. We're told that when we have a 0.52 kilogram mass with a time period of 0.86 seconds when it's attached to the spring, that means we can rearrange our equation to make K the subject, which is the only thing we don't know, and we can plug our values in to find K. Okay, so that's the first thing we can do. And then we know that that stays constant throughout the whole thing. Doesn't matter what the object is. This is the spring constant. And we can then use that K value to find our mass of the wooden block, which we're told the time period of, but not the mass. Okay, so this time we're just rearranging our equation again, but making mass the subject of the equation. And when you do that, you get 0.39 kilograms. So I'll just hold it there if you need to pause. Okay. In the next bit of the equation, it asks you for the total energy in the oscillation of the wooden block when it has been displaced horizontally by 4.8 centimetres. So, data booklet again gives you the total energy stored within a mass spring system at most, where omega is 2 pi over t, and we can calculate that because we were given the time period for the wooden block. That was the 0.74 seconds. So that's omega, but don't forget to square it in the equation. And then this 4.8 is your maximum displacement. That is your x0. Again, don't forget to square it. And then you're just plugging your numbers in and you get your 0.032 joules. Okay, the next bit was a bit more conceptually challenging, I think. Sorry, wait for the camera to focus itself. Come on. Okay. So a second identical spring is placed in parallel, and then we repeat the same experiment. Okay, so we oscillate our mass backwards and forwards with the 2 springs now. Suggest how this changes the fractional uncertainty in the mass of the block. Okay, so now the mass has a force that it is exerting, but it's now doing that on 2 springs rather than 1. So effectively the stiffness of the spring system will get larger. Okay, it'll be harder to extend those springs out now that there are 2 of them to do that with in parallel. Okay, so the spring constant will increase. So directly look at your equation here. If our K value gets bigger, then T gets smaller. Okay, so that means that our fractional uncertainty in T will be larger, and that's what we're measuring in order to calculate the mass, and so therefore we also have a bigger uncertainty in M as well. Okay, so I'm just going to pause there. Oh, I've chosen 2 highlighter colours that are too similar, sorry. That's like a turquoise, that's like a light blue. So we've got a graph of distance. So imagine your spring, this is like the left hand side of your coil, this is the right hand side of your coil. This means displacement to the left, so it means a point on the coil is moving to the left if it's down here, and anything up here means the coil is moving to the right. Okay, so this is at 1 instant in time, and if the wave is moving to the right, then we know that at some short time later the wave will have shifted to where I've drawn this dotted line. Okay, and it says state the direction of the motion of P on the spring. Okay, so at the instant you can see, P is positioned at the equilibrium point. Okay, now this is a set distance that P sits at on the spring. That's where it is in the spring. Okay, sometime later it has to be at this position, okay, on the wave, because it always has to be that P is showing somewhere along this line. Okay, so imagine it's oscillating to the left and to the right. Okay, and sometime later it's down here. That means it has moved further to the left, so it just moves to the left. Okay, now the next question on the next page needs a bit of explaining with this graph, so I'm going to look at it here. We're looking at P. Okay, anything that is physically on the right hand side of P, so if we think about our spring and assume that P is here, okay, anything physically to the right of P is above and therefore has been displaced further to the right. Okay, so these bits are extending outwards to the right. Anything physically to the left of P, so here, has been displaced down to the left. Okay, so that has moved this way. So this is where we take this spring and we stretch it out this way. Okay, so that must mean P is in the middle of where it's really stretched out, and that's a rarefaction. So literally this bit here says explain whether P is at the centre of a compression or a rarefaction. We know that the coils on the right hand side of P are moving to the right, and the coils on the left hand side of P are moving to the left, therefore we must be at the centre of a rarefaction. Okay, pause if you need to. Finally, we're at the last question. My goodness, I can stop talking soon. So monochromatic means one wavelength, all in phase. Okay, it's light from 2 identical lamps arriving on a screen. Don't get confused. There is no double slit here. This is just 2 torches, effectively. Okay, imagine having a torch in each hand and shining it on the wall. you know that you just see a lot of bright light, okay? It effectively makes it brighter. You don't start seeing fringes without those slits. Okay, so the intensity of the light on the screen from each lamp separately is I0. Okay, sketch a graph to show the variation with distance x on the screen. Well, effectively what you've done is you've doubled the amplitude from here. Okay, you've got 2 lamps, so therefore you're just going to have 2 lots of your original intensity. You've got double the intensity there. Okay. Go on, go and focus. Now we introduce some slits. Okay, we've got monochromatic light from one source, double slits, and we're told the slit separation, which is d, we're told the wavelength, lambda, and then the distance to the screen is capital D. It says that the intensity of light I at the screen from each slit is I0. Sketch on the axes a graph to show the variation with distance x on the screen. Okay, so we know that intensity is proportional to amplitude squared. Okay, now where light interferes constructively, the amplitude will double. Okay, and so at that point the intensity will be 4 times the original, and so the central maxima will be at 4I0. Okay, now the examiners would allow either of these patterns. You could have just had the simple double slit pattern, and this is without the modulation. Okay, so no single slit modulation, so that's just backwards and forwards up to 4I0. But you did need to work out the separation between your fringes by plugging your numbers in. So you're told the wavelength of light, you're told the distance to the screen, and your slit separation. So this is 2 centimetres that you calculate for your bright fringe separation. Hence why you can see at multiples of 2 you've got your peaks. Okay, but they also accepted that you may have drawn the modulated pattern, so you've got your bright central maxima and then the intensity goes down for your outer fringes. And then last but not least, you've got the slit separation is increased, outline 1 change observed on the screen. Well, if the slit separation is increased, that's little d, then this whole thing has got smaller. Okay, so S will get smaller, so the separation between fringes will get smaller. The bright and dark fringes will therefore be closer together. And we're finally done.